let yourself settle. There's nothing you need to hold on to here, nothing to memorize, nothing to prove you've understood. This is simply a space to rest while quiet ideas move slowly through the air around you. We're going to explore a question tonight, a question that doesn't demand an answer, but rather invites us to wander through possibility. What would happen if we stopped all carbon dioxide emissions tomorrow? Not in the real world, where such a thing would be impossibly complex, but in the careful, patient world of scientific thought experiments. A place where we can slow down, where we can imagine. This is a question scientists have asked themselves, not because they expect it to happen, but because asking it reveals something. Something about how the Earth works, how the atmosphere works, how the oceans work, how time itself moves differently in the climate system than it does in our days and weeks. Take a breath. There's no hurry here. The question itself is almost like a stillness, a pause button pressed on the entire industrial world. All emissions stopping at once. It's not realistic, but it's scientifically valuable. It shows us the shape of things, the momentum already in motion, the commitments already made. Scientists call this the zero emissions commitment, the climate change that would still occur after all carbon dioxide emissions cease. It's abbreviated as ZEC if you need a term to hold gently in your mind, though you don't need to hold it at all. You can let it go. The zero emissions commitment, the change that continues after the changing stops. There's something almost peaceful in that idea, not in what it represents, but in its simplicity, its clarity. Stop all emissions, watch what happens, measure what continues, let that thought rest for a moment. Scientists have done this work. They've built careful models. They've run simulations. They've watched virtual Earths respond to this sudden impossible halt. And what they've found might surprise you, or it might not. Either way, there's no test later. No need to remember the details. What they've found is that the Earth would largely stabilize, not cool down, not return to the past, but stabilize. The temperature would stop rising more or less, within years, within decades. It would find a new level and rest there. This is what recent assessments from the Intergovernmental Panel on Climate Change suggest, that the zero emissions commitment is likely close to zero on decadal timescales, meaning the temperature wouldn't continue climbing significantly after emissions stopped. It would stabilize rather than spiral. Stabilize, that's the word. Not reverse, not recover. Stabilize, like a pendulum coming to rest, like water finding its level. There's time here to let that sink in, or not sink in, to let it move past you like a slow current. The Earth would stabilize, the warming would stop more or less, within decades. You don't need to understand why yet, you don't need to understand how. We'll drift through those ideas slowly, the way night drifts into deeper night. This scenario reveals fundamental behavior, the way the climate system responds to changes, the way it carries momentum, the way it remembers, and the way it eventually slowly finds equilibrium. The Zero Emissions Commitment Model Intercomparison Project. Scientists gave it that formal name, ZECMIP. A collaboration designed specifically to answer this question with as much precision as current knowledge allows. They compared models, they compared predictions, they looked for patterns in the mathematics of Earth's atmosphere and oceans, and what they found, again, is that stabilization, that near-zero commitment to additional warming once emissions stop. It doesn't mean reversing climate change. Let that distinction rest in your mind without effort. It means stopping further warming, halting the rise, not erasing what has already occurred, but preventing what hasn't yet occurred. The difference is important, but you don't need to grip it tightly. It can float there. Imagine the Earth's temperature as a line rising on a graph. In this scenario, that line would level off. It would plateau. It wouldn't fall back down to where it started, at least not for a very long time. But it wouldn't keep climbing either. Current scientific consensus holds this to be true. Temperature would stabilize within decades rather than continuing to rise indefinitely. Within decades, not immediately, not overnight, but within a time frame that is, in climate terms, remarkably quick. In human terms, it's a portion of a lifetime. In Earth's terms, it's barely a breath. Let yourself rest in that time frame. Decades, this slow time, the time between generations, there's something almost gentle about the word stabilize. Even if what it's describing isn't entirely comforting, the temperature would stabilize at a new level, a warmer level, a level we're still adjusting to. But it wouldn't run away. It wouldn't spiral into runaway warming. This is what the models show, what the physics suggests, what the careful, peer-reviewed science has converged upon. You can hold this lightly, or not at all. So we stop. In this thought experiment, we stop everything. Every car, every factory, every power plant burning coal or gas or oil, every airplane, every ship, every breath of carbon dioxide from human industrial activity ceases. Tomorrow, right now, this moment, and in the hours that follow, in the days that follow, something would begin to change. Not the climate, not yet, but something closer, something more immediate, something you could feel if you were standing in certain cities, breathing certain air. The air itself would begin to clear. This is one of the most immediate effects of stopping fossil fuel combustion. The air quality would improve, not everywhere, not uniformly, but in the places where fossil fuels had been burning, where pollution had been accumulating, the atmosphere would begin to respond within hours, within days, within weeks. Fine particulate matter, nitrogen dioxide, ozone pollution from fossil fuel burning. All of these would decline rapidly. Let that image settle. Air clearing, skies becoming more visible, breath becoming easier. It's not about carbon dioxide yet. Not in these first hours and days. Carbon dioxide doesn't work that quickly. It doesn't clear from the air the way smoke clears from a room. It stays. It lingers. It has an atmospheric lifetime measured not in days or weeks, but in hundreds of years, in thousands of years, so the carbon dioxide would remain. The concentration in the atmosphere would stay elevated at current levels, initially unchanged by the cessation of emissions. The greenhouse effect would continue. The warming already in motion would continue its slow momentum. But the other things, the particulates, the nitrogen oxides, the pollution that comes directly from combustion and lingers for shorter times, those would begin to diminish almost immediately. Air pollution, as we currently experience it, contributes to millions of premature deaths annually. The number is staggering if you hold it in your mind, though you don't have to hold it. Approximately 6.7 million premature deaths each year, primarily from fossil fuel combustion. 6.7 million. Let that number exist without trying to comprehend its full weight. The health benefits from improved air quality would be immediate. They would occur in regions that had previously been burning fossil fuels, in cities, in industrial areas. Where combustion had been constant, its cessation would bring relief measured in clearer air, easier breathing, fewer hospital visits. Nitrogen dioxide responds quickly to changes in emission sources. Particulate matter levels respond quickly. These are not substances that linger for centuries. They are the immediate exhaust of combustion, and when combustion stops, they begin to dissipate. Within hours, the air begins to clear. Within days, measurements would show the change. Within weeks, people would feel it. This is the most human-scale effect of stopping emissions, the most tangible, the most immediate. Not the climate, not yet, but the air, the breath, the daily experience of atmosphere. Let yourself imagine that for a moment, or let the image drift past without attaching to it. Cleaner air, clearer skies, not because of wind or weather, but because the source of pollution has stopped. But the carbon dioxide remains. This is important to understand, though understanding can be loose and gentle here. Atmospheric CO2 concentration would not drop immediately. It would not vanish with the cessation of emissions. It would persist, holding the greenhouse effect in place, keeping the planet's energy balance tilted toward warmth. The carbon dioxide has an atmospheric lifetime measured in thousands of years, not because individual molecules stay aloft that long, but because the system that absorbs and releases carbon dioxide operates on such vast timescales. The ocean absorbs it slowly, the land absorbs it slowly, and what gets absorbed can also be released, in a complex dance between air and water and soil and vegetation. So in these first hours and days and weeks, the carbon dioxide stays where it is. The greenhouse effect continues uninterrupted. The long-term warming continues its slow trajectory, guided by physics and ocean currents and the thermal inertia of an entire planet. But the air clears, the pollution drops, and people breathe a little easier. Let that duality rest. The immediate and the long term, the tangible and the invisible, the hours and the millennia existing side by side. There's no contradiction here, just different time scales, different processes, different parts of the same vast system responding at different speeds. The atmosphere responds quickly to some things, slowly to others, and the difference between those speeds is where this story begins to unfold. Months pass, years pass. Time moves the way time moves in climate science, which is to say slowly, measured in seasons and decades rather than heartbeats. And in this time, something begins to happen to the temperature, to the global mean surface temperature, which is the average temperature of Earth's surface, land and ocean combined. It begins to stabilize, not cool. Let that distinction be clear, not reverse, but stabilize. The temperature would begin to stabilize within years to decades. This is what the models show, what the physics predicts, what the zero emissions commitment research has carefully, painstakingly demonstrated. Within years to decades, that phrase again, the intermediate time, the time that's longer than a moment but shorter than a geological age, let it rest there. Why does the temperature stabilize? The answer is a balance. A delicate, almost miraculous balance between two competing processes, two tendencies pulling in opposite directions, and for a time, perhaps for a long time, they approximately cancel each other out. On one hand, there's continued ocean heat uptake. The ocean is still absorbing heat from the atmosphere, still drawing warmth down into its depths. This creates a cooling tendency, a pull downward on the surface temperature. On the other hand, there's continued carbon dioxide radiative forcing. The CO2 in the atmosphere is still trapping heat, still holding energy in the system. This creates a warming tendency, a push upward on the surface temperature. These two processes, ocean heat uptake and CO2 radiative forcing, they balance, more or less. Not perfectly, but closely enough that the net effect is near zero, near stability. The ocean continues to absorb heat. The atmosphere continues to trap heat. And between these two opposing forces, the surface temperature finds a temporary equilibrium. Temporary, but lasting. Lasting for decades, perhaps longer. There's something elegant in that balance if you can sense it without trying. Two vast processes operating on planetary scales happening to approximately cancel each other out. Not by design, but by the physics of water and air and energy. Let that balance exist in your mind like a stillness. The temperature stabilizes, it doesn't plummet, it doesn't surge, it finds a level and rests there. This is what the IPCC special report on 1.5°C warming assumed, that the zero emissions commitment is negligible, close to zero. They used this assumption to calculate carbon budgets, to determine how much CO2 could still be emitted while remaining below certain temperature thresholds. Carbon budgets, thresholds. These are terms from climate policy, but they're rooted in this physical principle that when emissions stop, temperature stops rising. The temperature stabilizes. But that doesn't mean the Earth returns to what it was. Let that sink in gently, without alarm. Temperature stabilization does not mean an immediate return to pre-industrial conditions. It doesn't mean the warming reverses. It means the warming stops increasing. We would be stabilizing at elevated levels, at whatever level the temperature has reached by the time emissions cease. If we stop at 1.5 degrees above pre-industrial, if we stop at 2 degrees above pre-industrial, wherever we stop, that's approximately where we stay, for decades, for the foreseeable human future. The ocean's thermal inertia is at the heart of this. The ocean is vast, unimaginably vast, and water has an enormous capacity to absorb and store heat. The ocean has been absorbing the vast majority of the excess heat trapped by greenhouse gases, absorbing it and holding it and slowly, very slowly, distributing it through currents and mixing. This process causes the climate system to respond slowly, not on the timescale of atmospheric chemistry, but on the timescale of ocean circulation. The ocean continues absorbing heat for decades, for centuries. The mixed layer of the ocean, the surface layer that interacts directly with the atmosphere, responds more quickly, tens to hundreds of meters deep, stirred by wind and waves. This layer equilibrates with the atmosphere on timescales of years to decades. But the deep ocean, the vast reservoir below, responds much more slowly, on timescales of centuries, of millennia. So the climate system has momentum, memory, inertia. It doesn't stop on a dime. It continues moving in the direction it was already moving, gradually slowing, gradually finding balance, but not immediately. Not overnight. Years to decades for the temperature to stabilize. Let that time frame rest in your mind. Not geologically long, but not immediate either. Long enough for children to grow up, long enough for forests to mature, long enough for societies to adapt or struggle to adapt to the new conditions. But stabilization, that's the key word. That's what the science shows. The temperature would stop rising significantly. It would find a plateau. It would rest there, held in place by the balance between ocean heat uptake and greenhouse gas forcing. No sudden cooling. Let that be clear too. There would be no dramatic plunge in temperature, no return to previous climate states in the near term. The warmth we've added to the system would remain. The changes we've initiated would continue for a time, but further warming would largely cease. Stabilization, not restoration, but stabilization. And in that stabilization, in that plateau, there would be something almost like rest. The system finding equilibrium, the temperature finding its level. Not the level we might want, but a level nonetheless. Let that thought settle. Months to years, years to decades. The climate stabilization begins, slowly, gradually, following the immense physics of oceans and atmosphere, finding balance in the schematics of heat and energy and planetary systems. There's time here, time to let these ideas drift, time to feel the slowness of it all, the way climate moves on scales that dwarf our daily experience but still somehow matter to the lives we live and the world we inhabit. The temperature stabilizes within years to decades, and the Earth begins to find a new equilibrium. Decades pass now. Time stretches into the longer rhythms. The rhythms of ocean currents and carbon cycles and the slow chemistry of atmosphere and water. We're still in this thought experiment, this quiet place where all emissions have stopped, where the temperature has begun to stabilize, finding its plateau. And now something else begins to happen. Something subtle. Something that operates on timescales even longer than temperature equilibrium. The atmospheric carbon dioxide itself begins to decline. Not rapidly, not dramatically, but gradually, slowly, the way geological processes work. The way the Earth's natural systems work when left to their own devices. Natural carbon sinks continue their work. The ocean continues to absorb CO2 from the atmosphere. The terrestrial biosphere, the forests and grasslands and soils, continues to take up carbon and store it in wood and roots and organic matter. These processes don't stop when human emissions stop. They continue. They've been continuing all along, even while we were adding carbon to the atmosphere. They've been working in the background, absorbing roughly half of what we emit, buffering the full impact of our emissions, and when emissions cease, these sinks keep working. The ocean and land currently absorb approximately 50% of anthropogenic CO2 emissions. Let that number rest gently. 50%. Half of what we emit never stays in the atmosphere. It's pulled down into oceans and ecosystems, temporarily removed from the air, temporarily because carbon cycles. It moves between reservoirs, between air and water and life, but on human timescales, on the timescales of decades and centuries, this absorption matters. It shapes the trajectory of atmospheric CO2, so the concentration would begin to decline, gradually, over decades. The curve that has been rising for over a century would finally begin to bend downward, not steeply, not quickly, but measurably, detectably. The rate of decline depends on several things: on the current CO2 levels, on the efficiency of the sinks, on the state of the ocean and the forests and the complex web of biological and chemical processes that move carbon through the Earth system. Natural removal is a slow process. Let that phrase settle. Slow, not rapid drawdown, not sudden correction. slow removal, operating on the timescales that nature operates on. The ocean shows decadal variability in its carbon uptake, driven by circulation patterns, by climate variability, by the same El Niño and La Niña patterns that affect weather, that affect temperature, that ripple through the entire system. Some decades the ocean absorbs more, some decades less. But on average, over time, the trend continues, carbon moving from air to water. As CO2 concentration increases, the efficiency of natural carbon sinks decreases. This is important, though you can hold it loosely. The higher the CO2 levels, the less efficiently the ocean can absorb additional CO2. Ocean saturation becomes a factor. Ocean acidification becomes a factor. The chemical balance shifts. So the removal slows as the concentration rises. But it doesn't stop. It continues, just less efficiently, less eagerly if we can attribute such qualities to chemical processes. Conventional carbon removal methods exist as well, though they're not part of this thought experiment where all human activity has ceased. But in the real world, reforestation, soil carbon management, wetland restoration, these currently remove approximately 2 gigatons of CO2 per year. 2 gigatons. Against the roughly 40 gigatons emitted annually in recent years, it's a small fraction. But it's not nothing. It's the work of ecosystems recovering, of land management practices changing, of nature being given space to do what it does. In our scenario, with emissions at zero, these natural processes would continue, perhaps accelerate as ecosystems no longer struggle against the tide of new emissions, but still, slowly, still over decades and centuries. CO2 remains in the atmosphere and oceans for thousands of years, even with natural removal processes working constantly. This is the reality of the carbon cycle, the long tail, the persistence. Individual molecules cycle through the system relatively quickly. But the excess we've added, the perturbation to the natural balance, that takes millennia to fully resolve. The ocean and atmosphere and land slowly find equilibrium again, but on timescales that stretch far beyond human civilization as we know it. Let that vastness rest. Thousands of years, the deep time that's hard to comprehend, impossible to fully feel, but real nonetheless. The atmospheric CO2 begins to decline, over decades, over centuries, bending the curve downward, not erasing it, not returning immediately to pre-industrial levels of 280 parts per million, but declining, moving in the right direction, at the pace the Earth can manage. There's something patient about these natural processes, something that operates without urgency, without haste. The ocean absorbs what it can absorb. The forests take up what they can take up. And slowly, carbon moves from where we put it back into longer-term storage. Decades. That word again. The intermediate time. Long enough to matter, short enough to imagine. The concentration declines. The sinks continue their work. And the atmosphere very gradually begins to heal. Not completely, not quickly, but begins. You can let that image drift through your mind, or not. You can simply rest here in the slowness of it all. In the geological patience of carbon cycles and ocean chemistry, the carbon declines over decades, over the long rhythm of Earth's natural recovery, and time continues its slow, steady passage. But temperature, we return to temperature, because even as the carbon begins to decline, even as the atmosphere very slowly begins to clear, the temperature doesn't simply follow. It has its own momentum, its own commitments. This is what scientists call committed warming. the additional temperature increase locked in by past emissions, locked in by the climate system's inertia. Even after atmospheric greenhouse gas concentrations stabilize, even after they begin to decline, the warming continues for a time, because the ocean is still responding, still equilibrating, still slowly absorbing the implications of the heat already trapped. Ocean thermal inertia. We've touched on this idea before, but it deserves more time, more attention, more gentle circling, because it's central to understanding why climate change doesn't stop the moment emissions stop. The ocean is the great reservoir of heat in the climate system. It absorbs the vast majority of excess heat trapped by greenhouse gases, not the atmosphere. The atmosphere is thin, relatively small in its capacity. It's the ocean, with its immense volume and water's high heat capacity, that stores the energy, and the ocean takes time to warm, time to equilibrate, time to come into balance with the atmosphere above it. Even with stabilized atmospheric CO2, the ocean continues warming. The deep ocean, in particular, continues absorbing heat from the layers above, and as it warms, as it releases stored heat back into the system through complex circulation patterns, it causes further surface temperature increases, decades to centuries. That's the timescale here, the timescale of ocean circulation, of water masses moving through the depths, carrying heat with them, slowly redistributing the energy trapped by our emissions. Climate models show that temperature continues to change for at least 100 years after emissions cease. At least. Perhaps longer, depending on the model, depending on the assumptions, depending on the complex interactions not fully captured by our equations. 100 years, a century, longer than a human lifetime, long enough that the people who see emissions stop would not live to see the temperature fully stabilize. Let that settle. The commitment extends beyond individual lives, beyond generations even. The choices made, or in this case the cessation of choices, ripple forward through time in ways that outlast their makers. Ocean circulation timescales mean that water masses can be out of contact with the atmosphere for over 1,000 years. Let that extraordinary fact rest in your mind. Over 1,000 years. Water sinking in the North Atlantic, travelling through the deep ocean, only returning to the surface after more than a millennium has passed. During that time, those water masses carry the memory of the temperature they had when they sank, the heat content they had, and when they eventually return to the surface, they bring that memory with them, affecting the climate of a distant future. The deep ocean continues warming, continues equilibrating with the atmosphere, over centuries, over timescales so long they're almost geological. Temperature stabilization occurs when the ocean reaches thermal equilibrium with the atmosphere, when the heat has been fully distributed through the water column, when surface and deep are finally in balance. But that takes time, so much time. In the decades after emissions cease, committed warming continues. The temperature doesn't spike dramatically, but it doesn't immediately flatten either. It continues rising, slowly, gradually approaching equilibrium, asymptotically moving toward its final resting point. The ocean is the reason. The ocean's vast inertia, its slow response, its patient, geological timescale. Let yourself feel the slowness of it, or not feel it, but simply rest alongside it. The way the ocean moves, the way heat diffuses through water, the way a perturbation ripples outward through time, taking centuries to fully resolve. There's no urgency here, just the deep physics of fluids and thermodynamics, the mathematics of heat transfer and circulation, playing out on planetary scales. The temperature continues to change, for at least a century after emissions cease, continuing its slow trajectory toward equilibrium. Guided by processes that began decades or centuries earlier, when the heat was first trapped, when the energy first entered the system. Committed warming. The warming we're committed to. The warming already in motion, already inevitable, already working its way through the system. Even with zero emissions, even with the best possible outcome in our thought experiment, the warming continues for a time, let that be clear, without it being alarming. Just clear. The physics dictates it, the ocean's inertia dictates it, and so the temperature, even while stabilizing, continues its slow rise for decades, before finally beginning to plateau in truth, before finding its equilibrium, before resting at the new level where atmosphere and ocean are finally, after so much time, in balance. Decades to centuries, the committed warming plays out slowly, inevitably, following the path laid down by emissions already past, and the Earth continues its slow adjustment to the new energy balance we've created, the ocean. We keep returning to the ocean, because it's not just about temperature, it's about chemistry, about pH, about the fundamental nature of seawater itself. Ocean acidification is another consequence of our emissions, another change in motion, another commitment extending far into the future. It's caused by CO2 absorption. The same process that helps remove carbon from the atmosphere also changes the ocean. CO2 dissolves in seawater and forms carbonic acid. The chemistry is straightforward, inevitable. More CO2 in the atmosphere means more CO2 absorbed by the ocean, means more carbonic acid, means lower pH. Lower pH means more acidic. The ocean is becoming more acidic, has been becoming more acidic throughout the industrial era, and even if emissions stop tomorrow, even in our peaceful thought experiment, that acidification wouldn't simply reverse. Recovery from ocean acidification would take centuries to millennia, even after atmospheric CO2 declines, even after the air begins to clear. The ocean holds the memory longer, centuries to millennia. Let those timescales rest. They're almost incomprehensible. Longer than civilizations, longer than empires, longer than recorded history. Deep ocean acidification would persist much longer than surface ocean changes, because the deep ocean, as we've discussed, moves slowly. Water masses sink, carrying their chemical properties with them, and those properties persist, locked in the depths, for centuries, over 1,000 years, that number again. The thermohaline circulation, the great conveyor belt of ocean currents, takes over 1,000 years to complete a full cycle. Water sinking in the North Atlantic doesn't return to the surface until it has travelled through the deep Pacific and back, and during that journey it retains its chemistry, its pH, its acidification. So even as the surface ocean begins to recover, as it equilibrates with a slowly declining atmospheric CO2, the deep ocean remains acidified, remains chemically altered, for centuries, for millennia. Once severely altered, the ocean would take many centuries to return to its pre-industrial state. Even after atmospheric CO2 returns to pre-industrial levels, which itself would take thousands of years, the ocean lags behind. It remembers longer. It heals slower. Let that patience, that geological slowness, settle in your awareness. The ocean doesn't hurry. It can't hurry. Its processes operate on their own timescale, indifferent to human urgency or desire. The timing of emissions reductions critically affects ocean acidification severity. This is important. The sooner emissions stop, the less severe the acidification becomes. The more time the ocean has to begin recovering, to begin re-equilibrating with the atmosphere. Early action matters more for the ocean than almost any other part of the climate system. Because the ocean's response is so slow, because its recovery takes so long, every additional year of emissions extends the commitment by centuries. Early carbon dioxide removal measures provide significantly greater benefits for ocean chemistry than delayed action. If we could somehow remove CO2 from the atmosphere, pull it back out, reduce the concentration more quickly than natural processes alone would manage, the ocean would benefit disproportionately. But even then, the recovery would be slow, even with active removal, even with intervention, because the ocean doesn't forget quickly, centuries to millennia. The ocean's memory extends through time in ways that are hard to hold in mind. But they're real. They're part of the commitment we've made, knowingly or not, by altering the atmosphere. In our thought experiment, with emissions at zero, the ocean begins its long, slow recovery. The surface begins to equilibrate. The deep ocean continues its slow circulation, gradually bringing its chemistry back into balance. But it takes time, so much time. Generations would pass, civilizations would rise and fall, and still the deep ocean would carry the chemical signature of our emissions, still acidified, still altered, still remembering. Let that image rest. The ocean, patient and slow, carrying memory through centuries, through millennia, healing at its own pace, which is the only pace it has. There's something humbling in that, something that puts human timescales in perspective. We move quickly, we change quickly, but the ocean moves at the speed of ocean currents, and that speed is measured in centuries. The acidification persists, the recovery is slow, and the ocean, vast and patient, continues its ancient cycles, changed but not broken, altered, but still functioning, slowly finding its way back toward equilibrium, over centuries, over millennia, in the deep time that stretches beyond our comprehension, but remains nonetheless real. Ice. We need to talk about ice, because ice has its own momentum, its own memory, its own commitments extending far into the future. Ice sheets respond slowly to temperature changes. The great ice sheets of Greenland and Antarctica, kilometers thick, containing enough frozen water to raise sea levels by dozens of meters. They don't melt quickly. They don't stabilize quickly. They have their own timescales, even with zero emissions, even with temperature stabilizing. The ice sheets would continue losing mass for centuries. Sea level rise would continue. This is one of the clearest examples of climate commitment. One of the most concrete, most inevitable consequences of past warming. The ice has begun to melt, and it will continue melting for a long time, even after the temperatures stop rising. Sea level commitment. Scientists have a term for this. The future sea level rise already locked in by past warming, already inevitable, regardless of what we do next. The ice sheets have been set in motion, and their motion continues for centuries. Let that settle. The rise continues for centuries, long after emissions stop, long after temperature stabilizes, the ice keeps melting, the seas keep rising, following the momentum established by decades of warming. Sea level rise will continue until and beyond 2300, even for scenarios reaching net zero emissions. The models are clear on this. The physics is clear. 2300, nearly 3 centuries from now, and still the seas will be rising. Let that time frame exist in your mind without trying to fully comprehend it. 2300, a date so far in the future it seems almost fictional, but the ice doesn't care about our sense of time. It melts at the rate physics dictates, the Greenland ice sheet, one of the 2 great ice sheets on Earth. Its contribution to sea level rise only stabilizes after approximately 100 to 200 years of zero or negative emissions. 100 to 200 years. And that's just stabilization, not cessation. Just the point where the rate of loss stops increasing. The actual melting continues beyond that, for centuries more, depending on the warming level reached before emissions stopped, depending on how much momentum has already been imparted to the ice. The West Antarctic ice sheet, particularly vulnerable, particularly concerning. Scientists worry about its stability, about threshold behaviours, about the possibility of collapse. If it collapses, it would result in approximately 3.3 metres of sea level rise. Over centuries, not overnight, not in a single catastrophic event, but over the slow, inevitable timescale of ice flowing toward the sea. 3.3 metres. Let that number rest. That's more than 10 feet. Enough to reshape coastlines. Enough to displace hundreds of millions of people. Enough to fundamentally alter the geography of Earth. Complete Greenland ice sheet melt would raise sea level by about 7.4 metres. Complete Antarctic melt would raise it by about 60 metres. 60 metres, almost 200 feet. Enough to submerge cities, nations, entire regions of human civilization. These are not immediate threats, not in our lifetimes, not in many lifetimes, but they're possibilities that extend from the warming we've already created, from the momentum already in the system. At current emission levels, the entire Greenland ice sheet could melt by year 3000. Year 3000, a millennium from now, a date so distant it barely seems real. But the ice is real, the physics is real, and the slow, inexorable process of melting continues. In our thought experiment, with emissions at zero, the rate would slow. The commitment would be less severe, but the melting would continue for centuries. The ice sheets don't stop on a dime any more than the ocean does. They have their own momentum, their own memory, their own slow response to the temperature changes we've already imposed. Let yourself rest in this slowness, the inevitability. There's no urgency in it, ironically, because it's already inevitable, already in motion. The ice will melt at the rate it melts. We can slow it by stopping emissions, but we can't stop it entirely, not for centuries. Arctic sea ice behaves differently. It stabilizes under zero emissions. It even appears to return toward pre-industrial levels when CO2 is sequestered, when carbon is actively removed from the atmosphere. This is one area of hope, if we can use that word gently. Sea ice responds more quickly than land ice. It forms and melts with the seasons. It's in direct contact with the ocean and atmosphere, and when those stabilize, it can stabilize too. Southern Hemisphere sea ice is different. It continues declining under zero emissions. It doesn't simply increase again when warming stops. The dynamics are more complex, less fully understood, but the trend is clear. Continued decline, Even with emissions at zero, let these differences rest. Arctic and Antarctic, sea ice and land ice, each responding on its own timescale, following its own physics, but all sharing one quality: slowness, slow response, slow recovery, slow commitment to changes already in motion. The ice melts for centuries, and the seas rise for centuries, long after emissions stop, long after temperature stabilizes, following the momentum we've created, slowly, inevitably, at the pace ice melts and water expands and glaciers flow toward the sea. Centuries, that word again. The long commitment, the long consequence, extending through time far beyond our ability to feel its full weight, but real, measurable, inevitable. The ice continues melting, the seas continue rising, for centuries to come. Beneath the frozen ground, in the vast expanses of the far north, in Alaska and Canada and Siberia, in the lands where winter is long and the soil stays frozen year-round, or used to stay frozen year-round, there lies something waiting. Carbon, ancient carbon, organic matter that has been locked in frozen soil for thousands of years, tens of thousands of years, since the end of the last ice age and beyond. Plant material, animal remains, the accumulated debris of ancient ecosystems, all preserved in the freezer of permafrost. Permafrost. Ground that remains frozen for at least 2 consecutive years. Soil and rock and ice and organic matter, locked together in a frozen matrix, stable for millennia, until now. As the Earth warms, the permafrost thaws, and as it thaws, the organic matter within begins to decompose. Microbes that have been dormant, waiting, become active again, and as they break down this ancient carbon, they release it back to the atmosphere, as carbon dioxide, as methane, as greenhouse gases that add to warming, that amplify warming, that create what scientists call a positive feedback, the permafrost carbon feedback. Let that phrase settle gently. A feedback, a process that reinforces itself. Warming thaws permafrost. Thawing releases carbon. Carbon adds to warming. Warming thaws more permafrost. And in our thought experiment, even with all human emissions stopped, this process would continue. The permafrost wouldn't simply refreeze. The warming already in the system, the temperature stabilization at elevated levels, would keep the thaw going for decades, for centuries, for as long as the temperature remains above the threshold that keeps permafrost stable. This feedback would continue even after human emissions cease, adding to warming, adding carbon to the atmosphere from a source entirely outside human control, a consequence of past emissions triggering a natural process that then sustains itself. Let that circle through your mind. We stop emitting, but the Earth continues emitting, from permafrost, from ancient stores disturbed by the warming we've already caused. Permafrost carbon. Feedback would directly add approximately 0.06 degrees Celsius to temperature. That's the estimate. 50 years after 1,000 petagrams of carbon emissions, the range is 0.02 to 0.14 degrees, a relatively small additional warming in the context of the several degrees we've already added. But not zero, not negligible. 0.06 degrees. Let that number rest without trying to feel its magnitude. It's small compared to the warming from our direct emissions, but it's additional. It's on top of everything else. It's a commitment that extends from our actions but becomes independent of them. Thaw lag effects contribute an additional 0.04 degrees, range 0 to 0.06 degrees. Thaw lag, the delay between warming and the full thaw response of permafrost. Even after temperature stabilizes, the permafrost continues thawing for a time, responding to warmth that arrived years or decades earlier. Lag, delay, memory. The same words we keep encountering. The Earth remembers. Its systems have momentum. They don't respond instantly. They carry forward the implications of past changes. This feedback is unlikely to change the assessment that zero emissions commitment is close to zero on decadal timescales. Let that caveat be clear. The permafrost adds warming, but not enough to fundamentally alter the near-term trajectory. Not enough to cause runaway warming in the decades immediately after emissions cease. But it becomes more important over coming centuries as the thaw continues, as more and more permafrost becomes unstable, as the carbon stores built up over millennia are released over centuries. The feedback becomes more important over time, growing gradually from a small effect to a potentially larger one. Though uncertainty remains large, the amount of carbon in permafrost is uncertain, the rate of thaw is uncertain, the proportion released as CO2 versus methane is uncertain, the regional patterns are uncertain, but the direction is clear. Permafrost thaws, carbon releases, additional warming occurs, even after we stop emitting. Permafrost carbon feedback can amplify both the transient climate response to cumulative emissions and the zero emissions commitment. Two technical terms, but their meaning is straightforward. The feedback makes warming greater, both during emissions and after emissions stop. Amplifies, reinforces, adds to. The permafrost is no longer neutral, it has become an active participant in the warming process, a consequence that becomes a cause, an effect that feeds back into its own origins. In our thought experiment, the permafrost continues thawing for as long as temperatures remain elevated, for decades, for centuries, slowly releasing its ancient carbon stores, slowly adding to the atmospheric burden of greenhouse gases. There's something almost eerie about this, carbon that has been locked away since before human civilization, since before agriculture, since the very end of the Ice Age, now being released, now entering the atmosphere, now contributing to a process that began with our emissions but continues beyond them. The permafrost remembers the cold, but it's experiencing warmth, and in that warmth it changes, it thaws, it releases what it has held. Only 2 of 18 Earth system models in the ZECMIP project included permafrost carbon feedback representation. 2 out of 18. Let that ratio settle. Most of the models that calculated zero emissions commitment didn't include this process, not because it's unimportant, but because it's complex, difficult to model, uncertain in its magnitude and timing, so the estimates we have may be incomplete, may be underestimating the full commitment, or may be overestimating it. The uncertainty goes both ways, but the process is real. The carbon is there, the thaw is happening, and it would continue happening even if we stopped all emissions tomorrow. Let that rest in your awareness. Another commitment, another consequence extending through time, another way the Earth system has momentum, memory, processes that continue long after the initial disturbance. The permafrost thaws, the carbon releases, and the warming continues, slightly, additionally on top of everything else, for decades, for centuries. Following the slow timescale of soil thaw and microbial decomposition, and ancient carbon returning to the atmosphere, slowly, inevitably. Another thread in the complex tapestry of climate commitment: life. We need to speak about life, about ecosystems and species and the intricate web of relationships that covers Earth's surface and fills its waters, because they too are responding, they too have been changed. And in our thought experiment, where emissions have stopped and temperature has stabilized, they too would continue their slow adjustment to the new conditions. Climate stabilization would provide net benefits to global biodiversity compared to continued warming. Let that phrase settle. Net benefits, not restoration, not a return to what was, but benefits compared to the alternative of continued temperature rise. Stopping further warming helps ecosystems, gives them a chance to adapt without the additional stress of constantly shifting conditions, gives species a target to aim for, climatically speaking, rather than a moving target that keeps accelerating away from their tolerances. Ecosystem recovery depends on stopping further temperature increases, on stabilizing conditions. Species can adapt to new conditions if those conditions become stable. Many cannot adapt to conditions that keep changing year after year, decade after decade, faster than their generation times, faster than evolution can work. But some climate impacts on ecosystems would be irreversible on human timescales. Let that truth rest. Irreversible. Not on geological timescales, perhaps, not over millions of years, but on human timescales, on the timescales that matter to us and to the species alive now. Recovery timescales vary widely by ecosystem type and degree of degradation. Some ecosystems can bounce back relatively quickly, within decades, within a human lifetime, grasslands, some forests, some wetlands. Others take much longer. Coral reefs, old-growth forests, peatlands. These are systems built slowly, over centuries or millennia. And when they're damaged, when they're disrupted by climate change, their recovery extends over similar timescales, if they can recover at all. Species extinctions cannot be reversed. Let that finality be clear. When a species goes extinct due to climate change or any other cause, it's gone. Permanently. Completely. No amount of climate stabilization can bring it back. Extinction is the ultimate irreversibility, the permanent loss. And climate changes contributing to extinctions now would contribute to more even with emissions at zero, as ecosystems continue adjusting to the warmth already in the system. Let that weight rest, but not too heavily, just as fact, as reality. Species are being lost, would continue to be lost for a time even with the best possible outcome, because populations that are already declining, that are already stressed, take time to recover, if they can. Stringent greenhouse gas mitigation generally brings net benefit to global biodiversity even with land-based mitigation efforts. This is important. Even if we use land for carbon removal, for reforestation, for ecosystem restoration, the net effect on biodiversity is positive compared to continued warming. The benefits of a stable climate outweigh the costs of land use change for mitigation. Generally, on average, though locally the picture may be more complex, beneficial effects of climate stabilization on biodiversity become more relevant in the latter half of the century rather than immediate term. Not immediately, not in the first years after emissions stop, but over decades, as the stability allows populations to recover. As ecosystems find equilibrium with the new conditions, the latter half of the century, the 2050s, 60s, 70s, when the full benefits of stabilization begin to manifest, when species have had time to adjust, to adapt, to find their new niches in the new climate, natural carbon sinks and their capacity are reduced by climate change. This creates positive feedbacks. Warming reduces the ability of ecosystems to absorb carbon, which means more carbon stays in the atmosphere, which means more warming, which further reduces ecosystem function. Positive feedback again, a reinforcing cycle. Climate change undermining the very processes that could help stabilize climate. But some natural carbon sinks increase with climate change. Negative feedbacks, in the technical language, processes that counteract warming rather than reinforcing it. Polar continental shelves, for example, as ice melts, as new areas of ocean become ice-free, primary productivity increases. Algae bloom. Carbon is absorbed from the atmosphere and sinks into the deep ocean. Boreal forests. As the climate warms, forests can grow in areas that were previously too cold. Trees spread northward, absorbing carbon, storing it in wood and soil. These negative feedbacks don't eliminate the problem, don't balance out the positive feedbacks, but they help, they buffer, they moderate. The carbon cycle is full of such feedbacks, positive and negative, reinforcing and stabilizing, all operating simultaneously, creating a complex balance that scientists are still working to fully understand. Ecosystem restoration requires native species and can prevent spontaneous recovery when degradation is severe. You can't just leave a damaged ecosystem alone and expect it to recover. Sometimes intervention is needed, replanting, reintroduction of species, active management. But with climate stabilization, with emissions at zero, the conditions for recovery improve, the moving target stops moving, and ecosystems have a chance, at least, to find their way back toward health. Not to their original state. That may be impossible. The species composition may have changed, the structure may have changed, the climate itself has changed, but towards some new state of health, some new equilibrium appropriate to the new conditions. Let that image settle. Ecosystems finding new balance, not the old balance, but balance nonetheless. Life adapting. Life persisting, life finding ways to continue in the new climate we've created. Biodiversity conservation measures function as climate regulation when they concern large natural carbon sinks with negative feedbacks. Protecting forests protects carbon storage. Protecting wetlands protects carbon storage. Protecting the ecosystems that help regulate climate is, in itself, a form of climate action. Conservation and climate stabilization work together, support each other, create synergies. In our thought experiment with emissions at zero, ecosystems would begin their slow recovery. Temperature stabilized, they would have conditions stable enough to adapt to. Species would shift their ranges, communities would reorganize, new assemblages would form, appropriate to the new climate. Over decades, over centuries, following the slow timescales of ecological succession and evolution, and the gradual adjustment of life to new conditions, some species would thrive, some would struggle, some would disappear. But overall, the trajectory would be toward stability rather than continued disruption, toward adaptation rather than accelerating stress. Let that thought rest. Life continuing, life adapting, not unchanged but continuing, finding ways to persist in the earth we've altered, slowly, gradually, following the ancient patterns of adaptation and resilience that have carried life through countless changes over billions of years. The ecosystems adjust, the species adapt, and life, persistent and creative, continues its ancient work of covering Earth's surface with the intricate patterns of biodiversity, changed but not extinguished, altered but not broken, slowly finding new equilibrium in the new climate. People, we need to speak about people, about human health and human systems and the societies we've built, and how they would respond in this thought experiment where all emissions suddenly cease. Because the effects wouldn't only be environmental, wouldn't only be about carbon and temperature and ice. They would be human effects too, immediate and tangible and felt in bodies and lives. The most immediate benefit would be to health, to human health, through improved air quality. We touched on this earlier, in those first hours and days when the air begins to clear, but it deserves more time, more attention, because the health benefits would be profound, would be measurable in lives saved, in suffering prevented, in the simple ability to breathe clean air. Immediate health benefits from improved air quality outweigh long-term climate benefits in near term. Let that phrase settle. Immediate health benefits, not decades from now, not in the distant future, but now, within days, within weeks, within months. The long-term benefits of climate stabilization are real, are important, but they accrue slowly, over decades and centuries. The health benefits from clean air arrive almost immediately. Economic benefits from avoided health costs and premature mortality would be substantial. Let that word rest. Substantial, measured in billions of dollars, tens of billions, hundreds of billions. The economic value of people not dying prematurely, not suffering respiratory illness, not missing work due to pollution-related disease. Health and economic benefits from improved air quality would occur within years to decades, not centuries, not the distant future. But within time frames, humans can feel and measure and build policy around. The value of health savings from improving air quality to limit warming to 1.5 to 2 degrees Celsius outweighs implementation cost by a factor of 1.4 to 2.45. Let those numbers exist gently. The benefits are larger than the costs, not marginally, not barely, but substantially. 1.4 to 2.45 times larger. More than pays for itself. More than justifies the transition on health grounds alone, even before considering climate benefits. Averted premature mortality from air pollution reductions would produce annual monetized benefits in hundreds of billions of dollars over the next few decades, hundreds of billions every year. Lives saved have economic value, crude as it is to measure in money, but real nonetheless, rising to several trillion annually by end of century. Trillion, with a T. The accumulated value of clean air, of prevented deaths, of avoided suffering, measured over decades and expressed in the cold language of economics. But beneath those numbers are people. Our children with asthma breathing easier, our elderly people living longer, our communities experiencing fewer emergency room visits, fewer respiratory crises, fewer premature deaths. Air quality benefits are immediate for regions reducing fossil fuel combustion. Immediate. The places that were burning coal or oil or gas, the cities and industrial zones, they would feel the difference first, would breathe easier first. Not everywhere equally. The benefits would be distributed unevenly. concentrated in the places that had the most pollution to begin with. But for those places, the improvement would be dramatic, noticeable, life-changing. Burning fossil fuels emits sulfur and nitrogen oxides linked to premature death, respiratory illness, and asthma. This is the mechanism. This is why the health benefits are so immediate. These compounds form fine particulate matter. They create ground-level ozone. They irritate lungs. They penetrate deep into respiratory systems. They cause inflammation, disease, death. And when combustion stops, when the source of these pollutants ceases, their concentrations drop rapidly, within hours, within days, and the health benefits begin to accumulate immediately. Let that image rest. Cities with clearer air, children playing outside without the same respiratory risk, hospitals with fewer emergency admissions for pollution-related illnesses. This is perhaps the most human-scale consequence of stopping emissions, the one that would be felt most immediately in daily life. Not the climate, not yet, but the air, the breath, the basic human need for clean atmosphere. In our thought experiment, this benefit would be universal in fossil fuel-using regions, would improve quality of life for billions of people, would prevent millions of premature deaths over the coming decades. Not in the far future, not in some distant scenario, but starting immediately. Starting the moment the last fossil fuel plant shuts down, the last car stops running, the last ship drops anchor, the air clears, and people breathe easier. Let that simple fact settle. In all the complexity of climate science, in all the long timescales and distant commitments, this one thing would be immediate and tangible and undeniably beneficial. Cleaner air, healthier lungs, lives saved, starting right away. But energy systems, we need to consider energy systems. Because stopping emissions doesn't mean stopping energy use, doesn't mean returning to a pre-industrial existence. It means transforming how energy is generated and used. Energy system transformation would require maintaining zero-carbon energy sources. Let that requirement be clear. In our thought experiment, emissions have stopped, but civilization continues. People still need electricity, still need heating and cooling, still need transportation, though perhaps reimagined. Zero-carbon energy sources would have to sustain modern society. Solar, wind, nuclear, hydroelectric, geothermal, whatever combination works, whatever can provide reliable power without combustion, without emissions, this is technically feasible. We know this. The technologies exist. The challenge in the real world is deployment speed, is investment, is political will. But in our thought experiment, all of that has somehow been overcome. The transformation is complete, and society continues. Changed, certainly. The economy restructured around clean energy, transportation electrified or hydrogen-powered, industry redesigned to operate without fossil fuel combustion, but continuing. People still have homes, still have jobs, though different jobs perhaps, still have the basic functions of modern civilization, powered by clean sources. Let that possibility rest. It's not a return to the past, not a regression to some imagined simpler time, but a transformation, a fundamental shift in how energy flows through society. No return to previous climate conditions means continued adaptation needs. This is important, even with emissions at zero, even with temperature stabilized. The climate has changed, weather patterns have shifted, sea levels are rising, will continue rising for centuries. adaptation continues, must continue, building seawalls, relocating communities, changing agricultural practices, managing water resources differently, preparing for heat waves and droughts and floods and storms. The need for adaptation doesn't disappear when emissions stop. If anything, it becomes more focused. Because the climate has stabilized at a new level, societies can adapt to that level, rather than constantly chasing accelerating changes. But adaptation is still necessary, still costly, still requiring planning and resources and political will. Let that reality settle. Zero emissions doesn't mean zero climate impacts, doesn't mean zero need for human response. It means stabilized climate impacts, predictable climate impacts, impacts that can be planned for rather than constantly escalating. There's a difference, and it matters, but adaptation is still needed. Economic systems would need to function without fossil fuel industries, without coal mining, without oil extraction, without natural gas processing. These industries employ millions of people globally, generate trillions in economic activity. In our thought experiment, they've ceased, and something else has taken their place. Clean energy industries, manufacturing for wind turbines and solar panels, installation and maintenance, grid management, energy storage. The economic structure has shifted, but economics continues, markets continue, trade continues, just powered differently, organized differently, operating within different constraints and possibilities. This is perhaps the most challenging aspect of the scenario to imagine, not the technical feasibility of zero emissions, but the social and economic transformation required. The political coordination, the international cooperation, the managed transition. But in our thought experiment, somehow it's happened. Somehow humanity has collectively decided to stop, and the systems adapt, the economy restructures, society finds ways to continue without combustion. Let that transformation exist in your imagination, or not. You can simply accept it as the premise of the scenario and move forward. The important thing is what happens next, what the Earth system does, what the climate does, what the long-term consequences are. Human systems adapt because they must, because there's no alternative in this scenario, and in adapting they find new forms, new structures, new ways of organizing life and work and energy and meaning. Changed, fundamentally changed, but continuing. People still wake up, still eat breakfast, still go about their days. The substance of daily life continues, powered by clean sources, adjusted to new climate conditions, but continuing. Let that ordinariness settle. Even in this extraordinary scenario, daily life remains daily. People adapt. Societies adapt. Civilization continues its endless work of reproducing itself, generation after generation, just without emissions, just without the constant addition of greenhouse gases to the atmosphere. And the Earth system begins its slow response to that cessation, begins its slow journey toward whatever new equilibrium awaits, while people live their lives, adapt, continue. As humans always have, uncertainty. We need to speak about uncertainty, because despite all the science, despite all the models, despite all the careful measurements and calculations, uncertainty remains. The sign and magnitude of zero emissions commitment remain uncertain despite recent progress. Let that acknowledgement rest. Uncertain, not unknown, not completely mysterious, but not certain either. Scientists have narrowed the range, have increased confidence, have converged on the assessment that ZEC is likely close to zero on decadal timescales. But the uncertainty hasn't vanished. It might be slightly positive. A small amount of additional warming even after the balancing of ocean heat uptake and CO2 forcing. It might be slightly negative. A small amount of cooling as the ocean effect dominates. Most likely it's near zero. But the exact value, the precise trajectory remains uncertain. Complex interactions between carbon cycle, ocean circulation and ice sheets not fully understood. Let that complexity rest. Not fully understood, science has come far, has learned much. But the Earth system is intricate beyond complete comprehension. The carbon cycle has feedback loops we're still quantifying. The ocean circulation has variability we're still characterizing. The ice sheets have threshold behaviors we're still investigating. We know much, but we don't know everything. Regional climate responses less certain than global average temperature. This is important. The global mean temperature might stabilize predictably, but what happens regionally is more variable, more uncertain. Some regions might cool slightly, some might warm slightly. Precipitation patterns might shift in ways harder to predict. Regional ocean currents might change, monsoon systems might adjust. The global average can mask significant regional variability, and that regional variability matters to people living in those regions, matters to ecosystems adapted to local conditions, matters to agriculture and water resources and all the location-specific aspects of climate. Let that uncertainty settle. We can predict the global average with reasonable confidence. Regional details are harder, more uncertain, more dependent on complex dynamics we don't fully understand. Tipping points and abrupt changes difficult to predict precisely. This is perhaps the largest uncertainty. The non-linear behaviors, the threshold effects, the possibility that some part of the climate system might respond abruptly rather than gradually. Ice sheet collapse, rainforest dieback, methane release from ocean sediments, shutdown of ocean circulation. These are low probability but high consequence possibilities that could change the trajectory dramatically. We think they're unlikely under zero emission scenarios, think the warming would be too limited, too gradual, but we can't rule them out completely. Can't say with certainty that stabilizing at current temperatures or slightly above eliminates all risk of abrupt changes. Let that possibility exist without alarm, but without dismissal either. The risk is probably small, but not zero. Previous research showed significant uncertainty even in the sign of the Z key. Let that history inform the present. Not long ago, scientists weren't sure whether zero emissions commitment was positive or negative, whether temperature would continue rising or begin falling after emissions ceased. The fact that we now have more confidence that we've narrowed the range is progress, real progress. But it reminds us how recently this uncertainty was even larger, how much we've learned in just the past decade or two, and how much might yet be learned that could shift our understanding again. The ZECMIP project was designed specifically to close knowledge gaps about temperature change after emissions cease. A coordinated effort, multiple modelling groups, standardised scenarios, all aimed at reducing uncertainty about this crucial question. And it succeeded in reducing uncertainty, in narrowing the range, in increasing confidence, but uncertainty remains. Different models give different results. the spread hasn't collapsed to zero. Only 2 of 18 Earth system models in ZECMIP included permafrost carbon feedback representation. We mentioned this before, but it bears repeating. Most of the models don't include all the feedbacks, not because scientists don't know they exist, but because they're complex to model, uncertain in magnitude, difficult to parameterize correctly. So the models might be missing pieces, might be underestimating or overestimating certain effects. The models are our best tools, but they're not perfect. They're simplified representations of an immensely complex system. Let that limitation rest. Models are useful, essential, but imperfect. Climate models show variable responses in magnitude and timing of processes after emissions cease. Variable, not identical, not converging on a single precise answer, but showing a range. Distribution, a set of possibilities. From that range, we extract central estimates, likely values, best guesses informed by physics and mathematics in comparison with observations. But the range remains, the uncertainty remains, and honest communication of climate science requires acknowledging that. Decadal variability in ocean carbon sink suggests 10 to 40% of variability can be attributed to ocean processes. Let those percentages exist gently. The ocean doesn't absorb carbon at a constant rate. It varies from year to year, decade to decade, driven by circulation patterns and climate variability. 10 to 40%, a substantial range, meaning the trajectory of atmospheric CO2 decline after emissions cease would have natural variability superimposed on the long-term trend. Some decades faster, decline some decades slower. But overall, over many decades, the trend toward lower concentrations. The variability makes precise prediction difficult, but doesn't change the fundamental trajectory, doesn't invalidate the basic understanding. Let all this uncertainty settle in your awareness, not as doubt, not as reason to dismiss the science, but as honest acknowledgement of the limits of knowledge. We know much, we've learned much. The science has advanced remarkably in recent decades, but the system is complex, uncertainty remains, and probably always will to some degree. The best science can do is narrow the range, increase confidence, provide probabilistic estimates rather than certain predictions, and that's what it has done. That's what ZECMIP and countless other research efforts have accomplished. Narrowing uncertainty, increasing understanding, giving us a clearer picture of what would happen if we stopped all emissions tomorrow. Not a perfect picture, not a complete picture, but a much clearer one than we had before, and clear enough to act on, clear enough to inform decisions, clear enough to understand the basic trajectory, even with uncertainty remaining. Even with questions still open, the picture is clear enough. So we arrive, finally, at the end of this thought experiment. At the conclusion of this imagined scenario where all emissions stop tomorrow, where humanity collectively ceased adding carbon dioxide to the atmosphere. And what have we found? What does the science tell us about this impossible but illuminating question? A new equilibrium, not a return to the past. Let that phrase settle one more time. A new equilibrium. The Earth would stabilize at a different state than it began. Warmer than pre-industrial. Changed in fundamental ways, but stabilized. Zero emissions would stabilize climate at a new, warmer equilibrium. The temperature would stop rising more or less, would plateau at whatever level it had reached when emissions ceased, 1.5 degrees above pre-industrial, 2 degrees. Wherever we stop, that's approximately where we stay. For decades, for centuries, for as long as the ocean takes to fully equilibrate with the atmosphere, for as long as the ice sheets take to respond to the warmth already in the system, for as long as the slow processes of the Earth system take to work through the implications of past emissions. Let that timescale rest. Centuries. The new equilibrium would persist for centuries, would be the climate that future generations inherit, would be the world they adapt to, live in, build their civilizations within. Recovery to pre-industrial conditions would require active carbon removal over centuries. Let that requirement be clear. Natural processes would begin reducing atmospheric CO2, would slowly draw down the excess, but slowly. So slowly that returning to pre-industrial levels would take thousands of years. If we wanted faster recovery, we would need active intervention, carbon dioxide removal, technologies or land management practices that pull CO2 from the atmosphere faster than natural processes alone, sustained over centuries, a commitment as long as the commitment we've already made by emitting. But that's not part of our thought experiment. In our scenario, emissions have stopped. Full stop. No removal, no intervention, just cessation. And the Earth system responds in its own time, at its own pace. Many impacts would persist for centuries to millennia. We've walked through them slowly. Sea level rise, ocean acidification, ice sheet loss, deep ocean warming, permafrost thaw, each operating on its own timescale, each continuing long after emissions stop, long after temperature stabilizes, centuries to millennia. Let those words wash over you without trying to grasp their full weight. Time scales longer than civilizations, longer than empires, longer than most of recorded human history. The scenario demonstrates that stopping emissions halts further warming but does not reverse past changes. This is perhaps the central message, the most important understanding to take away, if you take anything away at all. Stopping emissions helps immensely, prevents continued warming, prevents acceleration, prevents the worst-case scenarios, but it doesn't undo what's already been done, doesn't reverse the warming already in the system, doesn't restore the ice already melted, doesn't return the ocean to its previous chemistry. It stops things from getting worse. And that matters, that's valuable, that's worth doing. But it doesn't make things better, except in the sense of preventing additional harm. Let that distinction rest. Stopping harm is not the same as healing, though it's necessary for healing to begin. Temperature stabilization occurs within decades. We've said this several times now in different ways. Let it settle one final time, within decades. Not immediately, not centuries from now, but within a time frame that's climatically rapid, even if it's humanly slow. Within decades, the temperature finds its plateau, and from that point, the slower processes begin. The ocean continues equilibrating, the ice continues responding, the carbon cycle continues its slow work, but the temperature itself, the global mean surface temperature, stabilizes, holds steady, gives ecosystems and societies a stable target to adapt to rather than a moving one. And in that stability there's something, not comfort perhaps, not satisfaction, but something approaching predictability, the ability to plan, to adapt, to build for a climate that isn't constantly shifting beneath your feet. Ocean and ice sheet responses continue for centuries even after atmospheric stabilization. The atmosphere stabilizes within decades, but the ocean takes centuries, the ice sheets take centuries to millennia. They're responding to warmth that's already occurred, to temperature changes already in the system, and their response times are measured in the movement of deep ocean currents and the flow of glacial ice. Slow, inexorable. Following physics that operates on timescales we can barely comprehend but must nonetheless acknowledge. The ocean warms for centuries, the ice melts for centuries, the sea level rises for centuries. All consequences of the warming that occurred before emissions stopped. All commitments already made by past actions, all momentum that cannot be quickly halted. Let that long tail of consequences exist in your awareness. The emissions stop, but the Earth continues responding for centuries, working through the implications of what we've already done. Achieving 1.5 degree scenarios requires reaching net zero CO2 emissions around 2050. This is real-world information now, not our thought experiment, but relevant context. In the real world, to limit warming to 1.5 degrees Celsius above pre-industrial, we would need to reach net zero emissions around mid-century, around 2050. Less than 3 decades from now, net zero, not zero. Net zero allows some continued emissions if they're balanced by removal, but the net effect must be zero. No further accumulation of CO2 in the atmosphere. That's the real-world challenge. That's the time frame that matters for meeting climate goals. Much sooner than our thought experiment imagines. Much more urgent than the question of what happens after all emissions cease. But our thought experiment illuminates what happens once net zero is reached. Once emissions and removal balance, the trajectory would be similar to what we've described: temperature stabilization, slow decline in atmospheric CO2, long-term commitments continuing. Natural carbon sinks remove CO2 slowly. We've said this many times, let it settle once more. Slowly. The ocean absorbs it gradually. The land takes it up gradually, over decades, over centuries, slowly drawing down the excess. Geological carbon storage provides effectively permanent removal, more than 1,000 years, if we could somehow inject CO2 deep underground into geological formations where it would mineralize. That would be permanent removal on timescales that matter to human civilization. Effectively permanent. Not truly permanent in the geological sense. Not eternal, but permanent enough. Longer than the rise and fall of empires. Longer than the span of human foresight. Let that possibility rest. Permanent removal is possible in principle, but it requires active intervention. Requires technology and energy and sustained effort. Doesn't happen naturally except on timescales of millions of years through rock weathering. Zero emissions commitment near zero means carbon budgets remain valid framework for climate targets. This is important for policy, for planning, for the real-world work of addressing climate change. If temperature stabilizes when emissions stop, then we can calculate carbon budgets, can determine how much total CO2 can be emitted while staying below temperature thresholds, can set targets and trajectories and measure progress. The near-zero ZEC validates this approach, confirms that the framework makes physical sense, that the budgets are meaningful. Let that technical point exist without needing to fully understand its implications. It matters for climate policy, for international negotiations, for the practical work of staying below temperature targets. But in our thought experiment, in our imagined scenario, the point is simpler. Emissions stop, temperature stabilizes, the Earth finds a new equilibrium, not the equilibrium we started with, not the climate of the pre-industrial era, but an equilibrium nonetheless, a stable state, a new normal, different from what came before, but stable enough to live in, to adapt to build civilizations within. Let that final image rest. The Earth at a new equilibrium, warmer, changed, committed to further changes that will play out over centuries, but stable in its average temperature, not spiraling, not running away, not continuing to warm indefinitely, stable, at a new level, with new conditions, but stable. And in that stability, the possibility of adaptation, of recovery where recovery is possible, of persistence where recovery is not. The Earth continues, life continues, human civilization continues, changed certainly, adapting to new conditions, dealing with the consequences of past actions, but continuing. The thought experiment ends here, with stability, with a new equilibrium, with the understanding that stopping emissions stops further warming, even if it doesn't reverse past warming, with the knowledge that the commitments extend far into the future, that sea levels will rise for centuries, that oceans will remain acidified for millennia, that ice sheets will continue melting long after the warming stops, but also with the knowledge that stability is achievable, that temperature can be stabilized, that the worst outcomes can be prevented if emissions stop, if we reach net zero, if we make that transition. Then the Earth responds slowly, following its own physics, its own timescales, its own inexorable processes, and finds a new equilibrium, not a return to the past, but an equilibrium nonetheless, a place where temperature stabilizes, where change continues but doesn't accelerate, where adaptation becomes possible because the target stops moving. Let that possibility rest. It's not a perfect outcome, not restoration, not reversal, but stability. And in climate terms, in the context of what could happen if emissions continued, stability is valuable, is worth working toward, is better than the alternatives. The Earth at new equilibrium, warmer but stable, changed but not changing further, committed to long-term responses but not committed to runaway warming. That's what would happen if we stopped all CO2 emissions tomorrow, not a return to what was, but a stabilization at what is, and from that stable point the slow work of adaptation, of living in the climate we've created, of building societies resilient to the changes already in motion for centuries, for as long as those commitments take to fully play out, but without further warming, without acceleration, without the worst outcomes that continued emissions would bring, stable, at a new equilibrium, not the ending we might wish for, but an ending that's livable, that's adaptable too, that allows for continuation. The Earth continues its ancient cycles, oceans circulate, ice flows, carbon moves between reservoirs, life adapts and persists at a new equilibrium, warmer, changed, but stable. And in that stability, the possibility of a future, different from the past, but a future nonetheless. Let that settle. Let it rest. Let the thought experiment dissolve. We've walked through what would happen, hour by hour at first, then day by day, then year by year, then decade by decade, then century by century. All the timescales, all the processes, all the slow responses of a complex system finding its way to equilibrium, and we arrive here, at this understanding, this knowledge, this picture of Earth at a new stable state. You don't need to remember the details, don't need to recall the numbers, don't need to hold on to any of it. Just let it wash over you, let it settle, let it exist as background understanding, if it exists at all. The Earth would stabilize, that's the message, the core truth, the scientific consensus. Stabilize at a new level, not return to the old level, but stabilize. And from there, the long, slow work of living in the world we've created for centuries, but without further warming, without runaway change, just the slow equilibration of a planetary system finding its balance. After we stopped adding to the imbalance, if we stopped, when we stop, the Earth would stabilize and find its rest at a new equilibrium. Let yourself rest now too. There's nowhere else to go in this thought experiment. No more timescales to explore, no more processes to examine. Just this final understanding, this quiet knowledge that stopping emissions would stabilize the climate, would halt further warming, would give the Earth a chance to find equilibrium, not perfection, but stability. And in that stability, the possibility of rest for the Earth and for you now, listening to these words. Rest. There's nothing more you need to understand, nothing more you need to remember. Just the slow rhythm of your breathing, the quiet space around you, the permission to drift, to let go, to simply be as the Earth would be, stable, at rest, at a new equilibrium. Let yourself find your own equilibrium now, your own rest, your own quiet place. There's nothing more needed here, nothing more required, just rest, gentle, quiet, rest.